All right, let's talk photoelectric effect. The photoelectric effect says that a light coming in hits a metal plate, and if it has enough energy, it'll release electrons, which we call photoelectrons. All right, so we go through a simulation. Here's kind of the picture of what it would look like, where I can vary the light coming in from the lamp, hitting a metal surface on the left, and those little dots are electrons that are released. And then I've got a little battery that sets up an electric field to kind of bias everything that's going on. If I take a look at this and I plot a graph of the kinetic energy versus the frequency of light hitting the metal, I get something that looks like this. And then I can keep changing the frequency, hitting the same metal target. And if I do that, nothing happens for a while until I get enough energy from the light, and then I get a line that goes up like this. It's a nice straight line. If it's a straight line, that means y equals mx plus b. But if I look at it, x is the frequency, and y is the kinetic energy. So really, this is kinetic energy equals slope times frequency plus the y-intercept. Well, this happens to fit our other equation that we know. The incident light, the kinetic energy of the released electron is equal to the incident light's energy plus the work function being that minimum amount of energy to hold it still. Remember, this kinetic energy is the energy of one electron leaving the plate. And the light is the energy of one photon hitting the light on the plate. And of course, the work function, that's the minimum energy needed to release an electron from the plate. So how does that work with the graph? Well, kind of nicely actually. The y-intercept on the graph is the work function. So I can take my straight line segment that's up at an angle and extend it down until it crosses the y-axis. And whatever my number is down there is the work function. Notice it's going to be a negative value because it's below 0. The instant energy that comes in, that's going to be along the x-intercept. And so what I know here is that F naught, that's the minimum frequency to provide enough energy to dislodge an electron with no extra kinetic energy. So it just releases it, doesn't go anywhere yet. So in this case, the incident energy is equal to the work function. Remember, our work function is negative, but when we do the calculations, we'll actually make it a positive value to make that frequency right. The slope, well, let's see, rise over run, that's going to be the energy divided by the frequency, and that's our equation E equals hf. So when I look at the slope and I rearrange it for h, that's Planck's constant, that's equal to the energy divided by the frequency. So this is how we use a graph in conjunction with the photoelectric effect.